Hi everyone, my name is Gregor Haas and I'm a grad student working in the HardwarE CyberThreat Research Lab, HECTOR for short, with Dr. Aiden Isu. In this lab, we work on analyzing the security of computer systems from a hardware perspective, very different from the typical view of hacking that you usually see in the media. I specifically work on analyzing the systems on a chip, or SoCs, found in iPhones, and my project actually did begin with some interesting software work. Apple locks down their platforms, making it really difficult to run custom code, which we often need to do for the types of experiments that we do at HECTOR. I'll cover some of these later. So, to get around this, I use a powerful exploit named Checkmate, which came out more than a year ago. Using Checkmate, I can then bootstrap a variety of research toolkits on iPhones, including a full Linux system. This software environment then lets me do experiments on Apple hardware, which Apple never meant for us to be able to do. My current research is focusing on what kind of cryptography Apple is implementing in HardwarE. The biggest target that we're looking at is the Secure Enclave Processor, or SEP, which is a dedicated CPU core inside of the iPhone's SoC. This CPU is in charge of all of your iPhone's security functions, from checking your fingerprint or face to log you in, to encrypting all of your files in a secure way, to making sure that the iPhone boots and turns on in such a way that makes the overall iOS system more secure. Specifically, we are looking at the hardware encryption engine built into the SEP. This encryption engine contains two secret keys which are fused directly into the hardware. No software can ever read them. One of these keys, the GID, is the same for each specific device model. This key, which Apple also knows, is used to decrypt various firmwares for hardware used by the iPhone. The other key, which is called the UID, is unique for each individual device and not known by Apple. This key is used to encrypt all of the files on the phone, so if an attacker, for example, tries to remove the storage chip from the phone and attach it to a different device, they won't be able to read any of your data because this different device has a different UID. So you can see, these two keys are pretty important for the overall system's security, and that makes them tempting targets for us.
We can't use any kind of software attack to get these keys, since they're completely isolated in hardware. Using Checkmate, however, what we can do is encrypt and decrypt whatever data we want with these keys. That's what you're seeing right now.
However, this encryption will still use a certain amount of power, and as it turns out, the amount of power used depends on the data being encrypted and the key being used. So, what we do is we instead look at the overall power usage of the phone. To do this, we can first inject power into the phone using a DC power supply and a battery connector, which we cut out of a real iPhone battery. Then, we insert a current probe in series between the power supply and the phone. This probe, when we then plug it into an amplifier and an oscilloscope, lets us measure exactly how much power the phone is using at any given time. Then, using Checkmate, we can start sending data to the phone and encrypting it with secret hardware keys. However, you have to indicate that precise point in time to the oscilloscope somehow, so it knows when to start measuring. For this, we use a small test point on the iPhone's logic board, which we can actually write to with software. This signal tells us exactly where in a power trace the encryption starts and ends. Then, with millions of these power traces and some advanced statistical analysis, we should be able to figure out the values of these secret UID and GID keys. We haven't been able to do this yet, but we think we're getting close, so stay tuned.